Okay, what we would like to do is introduce a little bit of notation so that we can state the things we've been doing in a lot more compact way so that we're not writing out things forever. First off, there's something called summation notation. You've seen this in your algebra classes. That's a big S for sum, by the way. That's not a big E. And what it basically says is add the following things that look similar. So for example, if I want to just put anything I want to here, like an n squared, and then I let's say n goes from 1 to say 10. What this tells us to do is plug in 1 and we get 1 squared. Once you actually plug it in and you still have stuff left because we're supposed to go to 10, the little counter goes up. It goes ching and n equals 2. Now that n equals 2, we plug it in. You can see that these things look similar because that's all this summation notation is good for, is adding things that are very similar. We're not to 10 yet, so we have to keep going. So we go ching, and n is now 3, and it goes on and on and on. And the very last thing we're supposed to plug in is 10 squared. Now, the nice thing about the summation notation is there's none of this dot, dot, dot stuff in the middle. The dot, dot, dot stuff is very imprecise, and it really gets in the way. So when we use summation notation, we like to do this so that we can write one thing and not have all this ambiguity in the middle. Now, meanwhile, we have two definitions that we've seen so far that involve lots and lots of sum. Yes, there's left n. Okay, I can see that. And remember, that looks something like r of t naught delta t plus r of t1 delta t plus, oh, there's the dot, 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 yes, plus r of the second last t, that's t n minus 1 delta t. Well, this is something that summation notation is very, very good at fixing. Because with all those things look very similar. So I'm going to write summation notation, which just means add all the following things. Every one of these things has an r. Every one of these things has a t on the inside. Every one of these things has a delta t. The only number that changes is the little subscript down here. And you can see that that subscript, I guess I'm going to use, how about, let's not use then. Let's use k. Yeah, that's it. Right. So k starts at 0. And k is going to tell us which term we're on, like that. And k goes all the way to n minus 1. And you can see this is a very, very short way of writing left n. Right n isn't much different. I'm just going to go right n like this. It's still going to be a sum. It's still going to be little rates times little times, or if you want, little heights times little widths. We're going to use both. This is still going to be r of tk, like that. There's still going to be a delta t, like that. But for right, k starts at 1 and ends at n, which I think feels better for most people. We have seen already that we need both, so it's not such a big deal. Now that we have summation notation, and like I say, we're not going to use it much beyond making our big long sums easier to deal with. We want to take what we've been doing and put it in context. Go back. So what we've had is we've had a rate graph. Now for this particular one, what I'm going to do is I'm going to call this t. I'm going to call this r of t. And I'm thinking this is feet per second, and this is seconds, right? It's just the easiest way to do. There's always been a starting time. There's always been an ending time. Now, I'm going to build this the same way you're going to build this in Calc 2, so we'll have seen it once. What I'm going to do is take a little chop, just like that. Yes, and I'm going to draw a teeny tiny rectangle right in the middle. Just like that. Boy, you can hear that squeaking. And what I'm going to do for my little tiny rectangle, that's funny, is to pretend and lie just for a second that the top is flat. Right? Now, if the thickness, which by the way is delta t, is really thin, you don't give the top much time to change y value, so it really does look really, really flat. Now, we had to take a chop at some location. I'm going to call it, I don't know, how about ti is the time at which we're making our chop. Now, the area of that little rectangle then is going to be r of ti times delta t, like that. So that's the area of the rectangle. You can also see, by the way, that that's a very small distance traveled, because this is feet per second, this is seconds. You multiply them together, you get feet. So this represents both the area of the rectangle and the little distance traveled from this time to this time. Now, what we wanted to do yesterday and the day before was to do this many, many, many times over and just add up all the results. So we either just added up a lot of areas, giving us an estimate of the area under the rate graph, or that same sum works as an estimate for the distance traveled. Now what we want to do is we want to be able to say that if we were adding up n of these, only putting in enough notation so I can live with it, if I'm adding up n of these, I get an estimate. If n gets really big, I get a really, really good estimate. And what we want to know is, what are the estimates getting close to? Well, this, like this, and like this, is going to be both the exact area under the graph, because that's what happens when you take limit of estimates. You get exact. It's also the exact distance traveled. So that's what tells us that the exact distance traveled is equal to the exact area under the graph. But we have some notation that, that we used with derivatives that we're going to also use here. Now, we had this principle that when we take derivatives of things with Greek symbols in them, after we take the limit, I didn't say that right. When we take limits of things with Greek symbols in them, after we take the limit, we replace them by their more modern counterparts. So when, for example, when we were taking limits of delta y over delta x, we got dy dx. We're going to do something very similar here. Instead of that Greek d, I'm going to just write a normal d. If the limit as n goes to infinity, the little I, which part of the top we're at, it completely loses significance. So the general notation for this is just r of t. Now, I'm supposed to replace that Greek s by its more modern counterpart. If this was being invented nowadays, you would write a regular old s. But this was done around 1700, and the s's didn't look like that. They looked like this, right? And so that's supposed to, what is that supposed to stand for? That's supposed to stand for the limit of the areas of the rectangles, the limit of the little distances traveled. So it's the exact area, it's the exact distance traveled. And this is going to be the notation for it because it's after the limit. Now, when we had the sums, we had a counter. I lost my counter because I took a limit. However, we still have a starting time and an ending time. So what I'm going to do is always put the starting time down there. I'm always going to call it A. It's the first letter of the alphabet, that's all. And we get a symbol for the exact distance traveled, the exact area under the graph, and this is called the Riemann integral. Riemann integral. And that's the definition of the integral. But what we always want to do is think of this in three things. It's the exact distance traveled, it's the exact area under the graph, and what we're going to often do, it's estimated by Riemann sums by areas of rectangles. So that's a little summary there.